All right, so we have officially begun. We don't have too many class periods left, right? We've got today and then Monday, and then the test is a week from today, next Wednesday. And that's actually the last official class day, except for the final exam, which is the following week on May the 11th. I need to check and see the exact time. It will be roughly class time, but so it'll be roughly 10 o'clock, but sometimes they slightly change the starting time. So it could be 9:30 instead of 10, or it could be 10:30 instead of 10, something. So I'll have to look and see. Yes, we'll still be splitting it in two. And is that right? Will we still be splitting it in two? I have to see what the time frame is. So I think so, but let me double check on that. Okay. So now for the test on next Wednesday, I did post the answers to the sample test. So the sample test answers are posted. We'll look at those in just a second. But now that will cover through this homework, which is due Monday. This is finding theories of polynomials, and which we've really now talked about completely, but I do have a couple more examples to look at. And then so we'll talk about then today and Monday these topics: rational functions, which are just an extension of polynomial functions. And so we're not going to spend a long time talking about rational functions. And then polar coordinates. So we'll finish the semester off switching gears slightly. So all semester we've been talking about rectangular coordinates, the Cartesian coordinate system, how you locate points on two-dimensional surfaces. But there are other ways of locating points on two-dimensional surfaces, or also three-dimensional spaces as well. And so we wanted to mention one of these alternative methods for locating points on two-dimensional surfaces, because these are, or in three-dimensional space, as I just said, because these alternative methods have advantages sometimes over rectangular coordinates. So they're useful frequently. And so we'll describe this other system called polar coordinates, maybe starting today. It depends on how far we make it in the notes. All right. So I know there are some questions on this homework, finding zeros of polynomials. So I'm gonna talk about a couple of those questions, but I have some examples in the notes first, which are probably similar to the questions you have on this homework. So before we look at that homework, I want to look at those examples. However, before any of that, let me mention again that the sample test answers are posted. So if you go to the usual spot, to the Blackboard page, here's the Blackboard page, to the sample test folder, and then there are the answers to the sample test. Now, I want to remind you that on the sample test, of course, you know, it appears kind of lengthy because, you know, it has lots of graphs in it. So it's not really as long as it appears because of all that blank space. And then if you go to the end, though, the last couple of pages, notice that these problems are about these last two topics that we have to cover: rational functions and polar coordinates. So those will be on the final exam, but not on test number 3. So starting on page 10, this material will be on the final exam, but not on test number 3. So you can save these pages to study for the final exam. Okay. So just the first few pages here, again, which will be material through finding zeros of polynomials. Okay. All right. Now, I will since we're not going to really have time to go over the sample test before the test, I will I'll make a tape of some of the highlights of the sample test, and I'll post that. But the sample test answer, okay. So, I mean, the solutions are there for you to use also. All right. I will talk about also Monday about preparations for the final exam. So we do have a review sheet for the final exam. And so I'll post that, and we probably can schedule a review session for the final exam, an optional review session for the final exam, since we don't have class on Monday, May the 9th. So that gives us an opportunity for having a review session for the final exam on that day, before the final exam on May the 11th. But I have to I have to make sure this classroom is available. So I'll have to reserve the room. Okay, because that's not officially a class day, so anything could be happening in this room on that time. All right. Let me go to the notes now before we go look at that homework, which is not due until Monday, but there is a homework due today, isn't there? Yes. Yeah, the first part of polynomials, right? So but we've looked at several of those problems, I think, already. But if you have questions from, yeah, on long division, which you use then for the homework that's due Monday, which is finding zeros, right? Okay. But let's look at this problem first, because there is a problem like this on the homework that's due next Monday. I think it may be the very last problem in the homework. This says find the coordinates of the points where these two polynomials intersect each other. So intersect means where the graphs cross one another, right? Okay. So now it may be that these graphs never cross each other, so it may be that there's no solution to this problem. But we can check that by actually making the graphs and looking to see if they really do intersect each other, and then think about how we would find those intersection points. So I have made the graphs already, so let me see if I can find those. I graphed these in Desmos. Let me is that this example? Yeah, I think it's this one. So there are the two functions, right? I think those are the ones. And so there's the graph of both of them, graphed simultaneously on the same set of axes. And so you can see they do cross each other, right? A few times. So so that problem does have answers. And now maybe those answers aren't that easy to find, right? Okay, but the problem does have solutions. Now, if you cannot find the solutions with pencil and paper so easily, then you do have the graphs here, right? So you could estimate the solutions to that problem by looking at the graph, right? And seeing if you can estimate the coordinates of these points. I see 3 points here where the where these polynomials appear to cross one another. Okay, so it looks like there's going to be 3 answers to that question. So if you're just stumped on how to answer that question analytically means with pencil and paper, okay, then you can resort to plan B, which is look at the graph, right, and try to estimate the solutions from the graph. Okay, and that also is easier said than done, but since we have these nice tools for making graphs of polynomials, then that certainly does make that approach to solving the problem, or at least estimating solutions to the problem, it makes it viable. Okay, right? If it was going to be hard to make these graphs, then that would be maybe not a solution strategy you would want to try to pursue, right? But since we can make the graphs easily, then maybe estimating the solutions from the graph is workable. But of course, that would just give us estimates, right? And our estimates might be quite good, but they would still just be estimates. So let's see if we can find the answers analytically, so we don't have to have estimates. We can find exact solutions. But I do want to point out now, however, and thinking about the analytical solution, the points where these graphs cross each other, right? The points where these graphs cross each other, notice that in those points, right? Of course, the X and Y coordinates, right? Have to fall on both curves, right? Okay, they have to fall on both curves, and that's kind of a clue to the analytical solution to this problem. Did I close my? I probably closed my folder there. Let's reopen it. Okay, got it back. All right. So so we've got these two functions, right? Let me rewrite these formulas slightly. Instead of using the function notation f of x and g of x, let's go back to kind of the old-fashioned notation where we just use y instead of f of x and g of x. And the reason I want to do that, again, is just to remind you that where these curves cross each other, right, at those points, where the curves cross each other, right, you know those x and y coordinates are solutions to both equations, right? So at those points where the curves cross, if you put the x coordinate in, right, to the right-hand side, right, then you get a y coordinate. And if you put that same x coordinate into the second formula, notice that the y coordinate in the second formula is going to turn out to be the same, right? Okay, because those points have to be on both curves. So what that tells you is then that since the y coordinates are the same, right, then you can equate these two expressions, 6x cubed minus x squared minus x plus 7. You can set that equal to the 24x squared minus x cubed minus 2x plus 5. This equation has to be true. This last equation has to be true at the points where those curves cross each other, right? Okay, correct? Because again, if you put the x coordinate in here and the x coordinate in here, you should get at the points where the curves cross each other, you should get the same y coordinate, correct? So these y values will be the same. That means then that these two expressions are the same as well, right? These two y coordinates would be equal at the points where the curves cross each other. So these two expressions would also be equal. Now, when you write down those two expressions equal to each other, of course, you get an equation, but you get an equation with just one variable in it, right? Okay, these two equations have two unknowns in them, but this equation only has one unknown in it. And so now you have a chance of solving this equation. But now you've got a big ugly equation here to solve, right? Okay, so maybe not easy work to solve this equation, but have a chance at it, right? Okay, you have an equation with one unknown that you want to solve. So I think we've talked about right at the beginning of the semester, but we may have forgotten it. I'd sort of already forgotten it, that we talked about it at the beginning of the semester. Remember, if you want to find the point where two curves cross each other, right? Okay, or the points where two curves cross each other, just take the formulas for the curves and set them equal to each other, and then try to solve that equation. And that will be at least the x coordinates of the points, right, where the curves cross. And you can plug those x coordinates back into either one of your functions to find the y coordinates for those points. All right, now, so let's see if we can solve this equation. What would be y'all's first step in maybe trying to solve that equation? See what cancels. But how do you see that, Rob? What cancels? They won't cancel each other, right? Because one's minus and one's positive. But that's a good that would be your first instinct, I agree. Okay, is to see what things cancel. But Robbie, you're correct. Actually, we are going to see what things cancel. But how do we tell what things cancel? What do you do with the equation to try to simplify the equation? Basically, determine what cancels. Yeah, right. Yeah, set everything to 0, right? So you're going to get all the terms, all the non-zero terms, Robbie, on one side of the equation, and some of those may cancel, right? Okay, so set the equation to 0. That's a typical first step in solving equations, right? Not always, right? But especially complicated equations, right? They want to set them to 0. So let's take all the terms on the right-hand side and let's move back to the left, right? So I have first all the terms that were on the left, right? And now let's move all of the terms on the other side, right? So now don't let me make a sign mistake because that will kill us. So when I move all these terms to the left-hand side, the signs have to change, right? So I get minus 24x squared plus 6x cubed plus 2x minus 5, and then all of this is equal to 0. And I don't think anything cancels, but we can combine terms, right? So we have 6x cubed plus 6x cubed, so that's 12x cubed. And then how many x squares do I have here? Minus 25? So minus 25x squared, and then what? Plus an x, and then plus a 2. Is that right? Equal to 0. Now I'm left with that ugly equation to solve. That's called the cubic equation because we have x raised to the 3rd power, right? So too bad it's not a quadratic equation because then we just be on our way, right? Okay, but now we have a cubic equation, and so now we have to think of this as a polynomial, right? Okay, and we want to think of solving this equation as finding the x-intercepts or the zeros or the roots of this polynomial, right? Okay, we want to find the x values that make this polynomial 0. That means you want to find the roots of this polynomial. But we are now really skilled at doing this, correct? Okay, so because we know where to look, right? So what are the possible rational? Maybe it turns out we won't have any rational x-intercepts. That would be unfortunate. But what are the possible rational x-intercepts of this polynomial on the left-hand side here? One of them is a half. Yeah, I think one of them is a half, but I think there are a lot of them, right? So let's write them all down, and then we'll have to just experiment, correct? So let's see, what are our p factors here? What are the factors of the constant coefficient? Yeah, 1 and 2, and then the factors of the leading coefficient. Unfortunately, there's a lot of those. 12 has lots of factors, right?
Yeah.
And that makes 12 a very useful number. And you know 12 is a useful number, right? Because English units of measure, right, are based on 12. And one of the reasons for that is because 12 has lots of factors, okay? So lots of them. So darn it, we end up with a big list of possible roots, correct? So God, what are all of those? Plus or minus 1, plus or minus 2. We can repeat these two, right? And now what else do we get? Have to divide 1 by all of these things, right? So you have plus or minus 1/3, plus or minus 1/4, plus or minus 1/6, plus or minus 1/12, right? And then you have to divide 2 by all of these things. So 2 over 1 is 2. I've already got that written down. 2 over 2 is 1. I already have that written down, right? But now you have 2 over 3. So that's 2/3. And then you have 2 over 4. That's 1/2. Do I have a 1/2 written down yet? Oh, I forgot it, didn't I?
Yeah.
So I should have written that one already down. So you have 2 over 4, which is 1/2. Then you have 2 over 6, which is 1/3. That one I did write down. And then you have 2 over 12, which is 1/6. That one I've already written down. Okay. Well, you've got quite a formidable list there of candidates for x-intercepts for rational x-intercepts for this polynomial, or in other words, rational number solutions to this equation. If we can find one, though, that's really all we need, because if we find one, we're going to be able to find the other two quickly, right? All right, so now this is where the guesswork starts. So y'all have to suggest something to me.
1/3.
I was afraid 1/3. Okay, all right. Why 1/3? All right. Well, then, well, at least you didn't say 1/12 because I didn't want to try one to start with. All right. So let's write down the coefficients here. So 12 minus 25, 1 and 2. Fortunately, there's no missing coefficients, right? And now let's do the synthetic division. So you bring down 12. 1/3 times 12 is 4. That's not bad. Minus 25 plus 4 is minus 21, right? 1/3 times minus 21 is minus 7. 1 and minus 7 is minus 6, and 1/3 minus 6 is minus 2. Wow, Amanda, your intuition is fantastic. Okay, so I'm so happy. So we found one immediately as 1/3. Okay, all right. Let's look at our graph. Let's go back at the graph and try to confirm that one. So that should be right here, correct? Does that look like 1/3? Let's click on that. Desmos is very friendly about, oh, there it is. It is 1/3. That was it. Okay. So so we found one, see. Wonder what this one is then. So what else could we have tried? What does that look like, guys? Minus 1/4 would have worked. And this one is 2. I thought for sure y'all would say 2 to start with. But I think this one is 2, right? Is it? Yeah, 2. Okay. Okay, so we've got 1/3. We know that is one of our roots, right? Okay, so one of the solutions to this equation. So one of the points where these curves intersect, right, begins with 1/3. And then to find the y coordinate, you just have to put the 1/3 back in. So you do have to put a little bit here. You have to put the 1/3 back into either one of these two equations, either one of these two formulas, right? To find the matching y coordinate. Now, what we're left with here, notice, is after we have factored out 1/3, see, we know now that this equation factors as x minus 1/3 times, and what's our remainder here? 12x squared minus 21x minus 6, right? And so to completely factor this, we just have to be able to factor 12x squared minus 21x minus 6. But I think that one we might be able to factor by inspection. So, but if you cannot factor that, remember, you can use the quadratic formula, okay? So because this is x squared, so the quadratic formula you can use to find other two solutions to your equation. Let's see. Wow. So how will this one factor? Let's see. I can cheat here. I know we're going to get x minus 2 as one of the factors. And then we must have what? 12x plus 3 is the other one. Is that right? Or 12x? Yeah, I think that's it. That's kind of a tough factoring problem. That would be a hard problem in a yeah, that would have been a while in an intermediate algebra class if I asked that. The students would take forever to factor that. Okay, they would never think of this combination, but that's it. X times 12x is 12x squared, minus 2 times plus 3 is minus 6, right? Then for the middle term, you would have what? Plus 3x minus 24x is minus 20. Okay, so there's the complete factorization from which you can find the other two solutions. One other solution is 2. And then the other solution is just set 12x plus 3 to 0 and solve, and you get what, minus 1/4? Yeah. So Oh, I overlooked something. We could have simplified this factoring a little bit by doing what? You notice the coefficients? What divides into all of those coefficients? 3. So we could have started this when we were factoring this set of parentheses. We could have started by factoring out a 3 first. That would have made it easier. Yeah, that would have made it a lot easier. But anyway, okay. There we got it. And now just plug, I'm not going to do it here, but just take these values, right, plug them into either one of the formulas to find the matching y coordinates. So do we have a problem on the homework that's like this one? I think so. But now maybe that one on the homework is not as friendly as this one. So let's go back and open the homework. Let's think about the problem from the homework. It's the last one. Yeah. Okay. All right. So on the same coordinate axis, sketch these graphs. All right. So we could graph those two. And then, oh, I see. So they're sort of guiding us through this, right? Anybody know which one is correct here? Guessing A there. It's got to be either this one or this one. Because when you graph minus x squared plus 11x plus 2, that is quadratic. So when you graph quadratic polynomials, you get parabolas. The curve is a parabola. That is a U-shaped curve because it has one turning. See, the degree is 2, so you can have one turning point. That turning point is called the vertex. So you've got to have a parabola. And since the leading coefficient is negative, the parabola has to open downwards. So only these two have parabolas that open downwards. So it's either got to be this one or it's got to be this one. Okay. Not sure of those two though, which one it is. So shall we just try one? So we can graph it with Desmos and look at Desmos. Did we get that right? Oh, we did. So it is this one. All right, so that's the tough one, right? Because that gives us 3 intersection points, right? Okay. But one of them appears to be 0. So, and that is correct. Because if you plug 0 in for x in this formula, what do you get for y? If you plug 0 in for x, this formula, what do you get for the matching y value? 2. And if you plug 0 into this formula, what do you get for the matching y value? 2, right? Okay. So that means that's an intersection point at 0 and 2. Okay. So that's a very useful. But nevertheless, how do we proceed from this point? What do you do? What are we doing? This is exactly the same problem that we just did. So
we combine.
Yeah, you combine them. So you take the two formulas and set them equal to one another, right? Okay. So you take the x cubed minus 2x squared minus x plus 2, set it equal to the minus x squared plus x plus 2, and then try to solve that equation. That equation will turn out to be easy to solve, though much easier than the one we just looked at, because the 2's will cancel each other. And so you will end up being able to factor out an x from, you'll be able to factor out an x, and then that makes it a lot easier to solve. Okay. So I think this problem number 9 you'll be able to do. Still have a chance to ask questions Monday. Ooh, now this one, okay. All right, so this one is a lot harder. All right, so, all right. I have an example like this one though. So let's look at the example first, and then we'll come back to this problem and see if we can tackle that problem. All right, here's my example. Okay, so see what this says. UHD has set aside a rectangular parcel of land. Okay, maybe it's right out there. A rectangular parcel of land to build a gator habitat. Okay, all right, so that'll be cool. All right, the area of the habitat has to be 5,000 square feet so that the gator has enough room there to survive. And so it says a diagonal between opposite corners. A diagonal between opposite corners. So you can see that diagonal drawn there, picture, will be 10 feet longer than one side of the parcel of land shown here. We want to find a polynomial. Zeros include the horizontal length x. All right, so there you see the horizontal length x in the picture. Where's my mouse there? In the picture, this is the horizontal length. Okay, there's the horizontal length, right? And we want to write down a polynomial somehow that, again, whose roots, right, include that horizontal length. So basically, I think they're asking us to write down an equation that includes x, that has x as its unknown, because I think from that equation, hopefully from that equation, we'll be able to derive a polynomial. All right, so let's see if we can get an equation, some sort of an equation involving x out of this picture. What immediately suggests itself to you when you draw that picture? I kind of have it really explicitly indicated there. I mean, what do you see in this picture when you draw a diagonal across a rectangle like this? Yeah, you see two right triangles. Sure, right. Yeah, you see two right triangles, right? So everything we know about right triangles applies here. Of course, we know lots about right triangles now, and we would know, so we could really do a lot of damage here in this picture if we knew anything about these angles, but we don't know anything about the angles, right? Okay, so I don't think trigonometry is really going to help us here too much, but that's okay. We know other things about right triangles as well. Going back to what's kind of our first piece of knowledge about the Pythagorean Theorem, which I think we proved on the very first day of class, right? So now here we are at the end of the semester, still using the Pythagorean Theorem. Well, that's not a surprise. So let's apply the Pythagorean Theorem to this picture, right? So the Pythagorean Theorem says, right, if you take the sum of the squares of the two sides, right? But I don't know the length of this side. This side I'm calling x. I don't know the length of this side, except this is a rectangle, not a square, right? So this does not have to be x. So I have to give it a name. So I'm going to call it y, just to give it a name that I can work with, right? So we know that x squared plus y squared is going to be the length of this diagonal squared, right? The hypotenuse of this right triangle squared. But I know something about that hypotenuse. That's x plus 10, correct? That's really helpful because that's really helpful, right? Because I don't want to have too many unknowns in my Pythagorean theorem equation here, right? So if I didn't know anything about the length of this diagonal, I would have to call it something like d, right? Or we often call that c, right? Because that's the hypotenuse of the right triangle. So I would end up with 3 unknowns here. And that's getting to be a lot of unknowns. But fortunately, I know this is x plus 10, so I've only got 2 unknowns. But Emil, that's still too many unknowns, right? Because I've got 2 unknowns, but how many equations have I written down so far? Just 1. See, that's not a good situation, right? I need another equation. I need as many equations as I have unknowns. But I haven't used all the information they gave me here, right? Because we were also told that the area of the gator habitat is going to be 5,000 square meters. So I know how to compute the area in this picture too, because this is a rectangle and we can compute areas of rectangles. We can also compute areas of triangles, right? We know how to do that now. And also, we also know areas of, we know areas of parallelograms too, didn't we? But this is only a rectangle. So what's the area here? X times Y is what? 5,000, right? Length times the width is 5,000. And now I'm feeling a lot better because now I've got two equations with two unknowns. So what I want to do is, you know, the usual thing, right? Solve one of the equations for one of the unknowns and then substitute into the other equation. Now, I don't know what the optimal way of doing that is, but I'm thinking solve this second equation for Y, right? Because that's really easy to do, and then substitute that into the first equation. So, and when you solve that second equation for Y, you get Y is equal to 5,000 divided by X. So in the first equation, I don't have to write Y anymore. I can write 5,000 over X. So I get X squared plus 5,000 over X squared is equal to X plus 10 squared, which by the way is X squared plus 20X plus 100, right? Now, Ravi, that is not a polynomial equation because why is that not a polynomial equation the way it's written? It is quadratic. It is well, kind of quadratic, but it's not even fair to call it quadratic because it's not a polynomial. Quadratic refers to polynomials, but this is not even a polynomial. It does have some x squareds in it, but this whole thing is not a polynomial. What prevents it from being a polynomial? What, this fraction, right? Remember, in polynomials, you cannot be dividing by x in polynomials, all right? Cannot be dividing by x. See, this is really a 5,000 squared over x squared. You'll have to tell me what 5,000 squared is in a second. So we have 5,000 squared over x squared is equal to x squared plus 20x plus 100. But and when you have x squared in the denominator, that's the same as x to what power? Not quite -1 because this is squared. So that would be x to the what? -2 power. In polynomials, though, you cannot have, you have x to whole number powers only. Whole number does not include negative integers. Okay, whole number means 0, 1, 2, 3. Might think of -2 as being a whole number, but mathematical terms, it's not a whole number. That's called an integer, but not a whole number. So anyway, this is not a polynomial. So the things we know about polynomials are going to apply here, right? So you have to be careful about that. But we're going to turn this into a polynomial really fast because what can we do to get rid of this fraction? Multiply everything by x squared, right? Okay, so just multiply everything on both sides by x squared. So when you do that, you get what? X to the 4th power, say I multiply this by x squared, right, is plus, here the x squareds will divide out when you multiply by x squared, right? So that would be 5,000 squared, right, equal to x to the 4th power plus what? Plus 20x cubed plus 100x squared. That is a polynomial, okay? See, that only has x raised to whole number powers. So, so we've got a, so we do have a polynomial equation here, and that's really the answer to the question. Just set this to 0. Just set this to 0, and you'll have what was asked here. Because you weren't asked to solve this problem. You were just asked to find the polynomial, right, whose zeros include x. So just set this to 0, and you're done. How do you want to set to 0? You all move everything to this side? Okay, so I get 0 is equal to, fortunately, the x fourths go away, right? So you have 20x cubed, no x to the 4ths, right? Plus 100x squared. And then, is that it, except for this? Minus 5,000 squared, whatever that big number is. 150,000 or 2,500,000 or something like that. Okay. There it is. So there it is. That's the polynomial. Wow, I wonder how we would solve that polynomial equation there. How would we find the roots to that? That's really terrible, right? Because here are methods for finding roots really don't serve us very well because this is such a large number. So it's going to have lots of factors, and it's going to be very difficult to determine, even want to experiment with in trying to find the zeros of this polynomial. But that's okay, because what can we also do? Graph, yes. Oh, so I'm glad you said that so fast. That makes me happy, because my students are really hesitant about graphing things. But we really mustn't be. Let's see if that's right. Is that it? It is it. I think I had divided everything by 20 to simplify the equation. Okay, so that's really essentially the same polynomial equation. And notice it does have a root. There it is. Okay, so right about there. So the length of that gator habitat is right at 106. Was it meters? Yeah, I think so. Okay, right. So the length there is 6 meters, approximately, right? Slightly more than 106 meters. Wow, that's kind of big. 6 meters. That's pretty good size gator habitat there. Okay. Now we can't, sadly, I don't think the university is allowed to keep gators. So I think there's a law against that. So there won't be a gator habitat. All right, let's see. Now let's go back to the homework and look at that last problem. Is that here? Oh, okay. So let's think about this problem, which is actually quite similar in a sense. So a box with a square base has a length plus the girth, and they explain the girth is the distance around the box. In this case, they mean this distance like this around the box. All right. So if you take the length there and then plus that distance around the box this way, of course, you could also go around the box the long way, but they mean around the box this way. Add those two things together, you get 104 inches. And they also say that the volume of the box is, in my version of the problem, 2,100 cubic inches. Okay. And they want to know then what is the length of the box. All right. So how do we set this up? So remember those numbers for me. Let's go back to the notes here and try to write this down. See if I can add some. You have to add some paper. Okay, so let's think about the girth of that box plus the length, right? So the girth of the box, again, you're going around this direction, not in the long direction to compute girth. So that would be basically that that base B in the picture repeated 4 times, right? See, the girth would be this length plus this length plus this length plus this length. All of those lengths are labeled B here in the picture. So you would basically have B plus B plus B plus B 4 times. In other words, 4 times B, correct? So the girth is 4 times B, but they want you to add on also what? The length, right? And that's supposed to come out to be equal to what? 104. So we get this equation, which has these 2 unknowns in it, but we need another equation, right? Because we've got only a single equation there. So the other equation has to do with the volume, right? And we were told in, again, the version of the problem that we're looking at there, that the volume was 2,100 cubic meters. But how would you calculate the volume of this box? Well, remember, to calculate the volume of a rectangular box like this, right, you have to multiply all the dimensions together. So we would have B here times B again, and then times L, all right? So that's the volume computation. So let's write that down. So B times L, right, is equal to 2,100. All right, so now we're in great shape there, right? See, we've got the 2 equations with the 2 unknowns. And now in the usual fashion, right, we have to boil that down to 1 equation with 1 unknown. We'll do that by substitution. Now you can do your substitution in a variety of ways, but I think what's convenient here, it turns out, in solving this problem is to take the first equation and solve it for L. That's kind of obvious, right? You would get L is equal to what? 104 minus 4B. And now take that and substitute it back here. So you get B times B, which is B squared, times the L, which is 104 minus 4B is equal to 2,100. And now we're feeling a lot better, right? Because this looks like a polynomial equation, except it has B in it instead of X. So when you multiply the B through the parentheses, you get 104B squared minus 4B cubed is equal to 2,100. And let's set that to 0. And I'm going to move all the terms over to the right-hand side just to make this leading term positive. So I have 4B cubed minus 104B squared plus 2,100 equals 0. And you can simplify that equation a little bit by dividing everything by 4. Divide everything by 4 just to make the equation easier to look at. And so you get B cubed minus 26B squared plus, what's 2,100 divided by 4? 525? And yeah, that's it. So there's the, there it is. There's the equation we want to solve. Now, how do we look for our rational solutions there? Yeah, we have to write down the factors of 525, and then also the factors of the leading coefficient. That's one reason I wanted to divide everything by 4, was to make that leading coefficient 1. Well, I'll write those down. So that's plus or minus 1. All right, now y'all have to write down these. Oh, okay. There's a lot of them, right? Okay, there's going to be a lot of them. Can you see something? Of course, a couple of obvious ones are plus or minus 1 and plus or minus 525. I don't think those are going to work. 5 and something. 5 and how many times does 5 go into that, Amanda? It's 105. Yeah. Okay. And then there's a bunch of other ones as well. All right. But what I would do is when I find something, when I recognize some factors here, just try it and see what happens. So I would try the 5 to begin with. Okay, that would be the first thing I would hone in on, and hope I would get lucky, and not have to write down all the factors of 525 because there are a lot of them. Yay! See, that works. Okay. So assuming that they're going to be merciful, I would try the 5 first because that's kind of the obvious, other than 1 or 525, right? That's kind of the obvious factor that might work, right? And it does work. So so this equation factors as b minus 5 times b squared minus 21b minus 105. And now you can use the, I don't think this is going to factor, but you can use the quadratic formula to try to find the other solutions. Okay. By the way, now if you are really stumped right here, and if you are really stumped right there, and you didn't really want to deal with trying to find the factors of 525, right? What could you have done at this point? Graph it, right? Okay, maybe the graph would be helpful, correct? So you might have been able to graph it and look on the graph. See if I have something that's easier to graph here. Let me try altering this graph. So so I can use f of x, that's fine, equals. Instead of b, let's use x cubed. So let's use x, in other words, instead of b as the variable. So what's the coefficient there? Just 1, right? And then there's some b squareds, aren't there? Minus 26, right? Minus 26. Is that right? And then is it plus 525? And then plus, where's the plus sign here? And then plus 525. And then look at the graph. Oh, I see. There is there's an x-intercept there. Not sure what that number is, but over here, whoops, there's another x-intercept you see, and I can very clearly see, ooh, that one is 5. So that might clue me in. Oh yeah, okay. Let's try 5, all right, and see if that one works. And then we can use the quadratic formula to find the other 2. So there are 2 other ones. One of them down here, I don't know what this number is, but we can point at it though. Oh, so something like minus 4.171, whatever that is. And then there's another one way over here, but you really have to look to find it. Ah, right there. At 25.171. So those you can find exactly using the quadratic formula once you have factored out the b minus 5. Okay. So see how to solve that one? So see, sometimes the graphs really are useful. Okay. All right, so that's all I want to say about that's all I'm going to say about polynomials. Do y'all have other questions from the homework? Either this homework or the homework, the prior homework? The one that's due tonight? None? Okay, I will leave it to you guys then to finish that. All right, let's go back to the notes and let's introduce our next topic before we take our break. So the next topic is rational functions. And so rational functions are formed from polynomial functions. The reason they're called rational functions is rational involves the word ratio, right? And rational functions are the ratio, the fraction formed from polynomial functions. Okay, so a rational function is of the form one polynomial divided by another. So we can frequently use our knowledge of polynomials to help us understand rational functions. Okay, so you have a polynomial in the numerator and a polynomial in the denominator. Whenever that happens, that's called a rational function. Now, the graphs of rational functions usually are messy. Okay, they're really messy. And all we're trying to understand today is a little bit about what the graphs, what we can expect the graphs to look like. Okay, when we graph a rational function. Let's take a look at a simple example. We have to start with something simple because the graphs can get really complicated really fast. All right. So this is about as easy an example of a rational function as right down. 3x plus 5 over x plus 2. So this is just an example. There's nothing special about that particular rational function, other than it's kind of simplified, right? Because in the top, you have a polynomial. 3x plus 5 is a polynomial. What's its degree? 1, yeah. So that's linear, but that's a polynomial. And in the bottom, you also have a linear polynomial. So you have degree 1 divided by degree 1. You know, that's kind of almost as easy as it gets, right? Okay. The quotient of two really simple polynomials. All right, let's see what we can discover about let's see what we can discover about this polynomial just based on the knowledge. I'm sorry, this rational function, not polynomial. Let's see what we can discover about this rational function just given the knowledge that we have now, without any special knowledge of what to expect from a rational function. So let's start with trying to write down some of the key features. And I would start with just what is the Y-intercept. Okay, so what's the Y-intercept here? Because that's easy to find for any function, right? So how do you find Y-intercepts? Just do what?
X0.
Make x 0. So when you make x 0 in this formula, y over 5 over 2, right? Yeah. So so it has a nice Y-intercept 5/2. So it's going to cross the y-axis at 5/2. Okay. Now, along with that, right? Okay. Let's write down the X-intercepts. So how do you find the X-intercepts? Of course, for any a function. You're thinking of inverse. Make y equals 0, right? So set the formula to 0, in other words, right? So you would write 0 is equal to 3x plus 5 over x plus 2. Evan, this does have an inverse, by the way. It will have an inverse, so you can find the inverse by switching x and y and then solving. But that's a little bit. That feature is a little bit beyond what we really need just to sort of get a basic understanding of the function, right? We don't really need to know what the inverse is. So just set it to 0 and try to solve this equation, right? Well, look, with a rational function, remember a rational function is going to be, its formula is going to be a fraction, because you always have one polynomial divided by another polynomial in the formula for a rational function. So when you're finding x-intercepts for rational functions, you'll always have a fraction equals 0. And how does a fraction equal 0? There's only one way for a fraction to equal 0. What must equal 0? Not the denominator, but the numerator, right? So really, to find the x-intercepts for rational functions, you really are just going to set the top to 0. Just set the numerator to 0. Okay? So you're really just solving this equation, 3x plus 5 equals 0, and that's easy to solve. What are the solutions there? Is that minus 5/3? I'm skipping a step there, but y'all can do that in your minds, I think, right? Just subtract 5 from both sides and divide by 3. So you get minus 5/3. Oh, so nice x-intercept. There's only one. Minus 5/3. By the way, in general, for a rational function, how many x-intercepts could you have? Remember, you're always setting the to find the x-intercepts for a rational function, you're setting the top to 0. The top is a polynomial. So you're really just looking for the x-intercepts of the numerator polynomial. But how many x-intercepts can the numerator polynomial have? It depends on what? The degree, right? So just look at the degree of the top. That will tell you how many x-intercepts you might have. Right? Okay. And here the degree is 1, and we have 1 x-intercept, just like expect. Now, there's one other catch with rational functions that you have to be careful of, that you don't have a problem with polynomials. Remember, for polynomials, the domain is all real numbers. For polynomial, the domain is all real numbers. So polynomials have very easy domains. But rational functions, their domains is not that simple, because the formula involves division, right? Okay. And remember, when you have a function formula that involves division, you have to be careful about the domain because it might be restricted. So what numbers can we not include in the domain here in this rational function? So what now? -2, right? Yeah, Robbie, -2. And how did you find that? By doing what? Yeah. Yeah, we put the denominator equal to 0, right? So to find the x-intercepts, we put the top to 0, but to find out the numbers not in the domain, right, we set the denominator to 0. So in other words, we look for the x-intercepts of the denominator, also a polynomial, so it may have several x-intercepts, right? And all of those x-intercepts cannot be in the domain, okay? So in this case, take x plus 2 and set it to 0, and of course you get x equal -2. So your domain is what? All real numbers except -2. So that's important to know, because when you graph this rational function, it's not going to cross this vertical line. Okay, the graph will not cross the vertical line x equals -2. Because that -2 is not in the domain. All right, now let's actually make the graph and see what it looks like. So we know something about what it looks like, right? We know what the y-intercept is and what the x-intercept is, and we know the curve will not cross over x equals -2. So there's going to be a break in the graph right there at x equals -2. Let me see if I can find my let me see if I can find this graph, if I can get the right thing up here. So I have that one kind of graphed here, and there it is. There's the graph. Okay. Not too exciting, right? But we weren't really expecting maybe too much out of that. So looks like this. And it crosses, there is, that must be 5/2, because that was the y-intercept, right? There is there's the x-intercept, so that must be -5/3. And notice you have a break in the graph at x equal -2. You have a break there in the graph at x equals -2. So the graph does not cross over that vertical line at x equals -2. So what the graph does, since it cannot cross over -2 here, notice that it kind of veers off, right? Okay. On the left-hand side, the y values start going up to positive infinity, and on the right-hand side, the y values start falling off to negative infinity. Notice the curve, of course, can get really close to this vertical line, but it can't ever touch that vertical line, because that vertical line at x equal -2 is not in the domain. Now, I want to point out something else in this graph, okay? Notice what's happening. Notice what's happening here as you get. Notice what's happening here again as you get close to -2, right, on the x-axis, as I mentioned. Notice the curve is shooting up there to positive infinity and going down to negative infinity on the right-hand side. But now notice as you get far out on the x-axis to the left-hand side, notice that curve also appears to be approaching a line here, right? In this case, a horizontal line right there, right? And whatever that value is, I'm not sure what that value is. 3. And notice the same thing happens over here on the far right-hand side as you move far to the right on the right-hand side. Also, the graph is sort of flattening out, right, and looking more like a horizontal line, and it's approaching it's the same horizontal line, isn't it? On the left and the right, and you guys are saying, I think it's 3, okay? So it looks like the graph is getting close to y equals 3, but it looks like it doesn't touch it, right? Looks like it's getting really close to it, but on the left and the right, it looks like never touches that. So I'm thinking that sort of indicates that the number 3 is not in the range of this function, right? It looks like y equals 3 is not in the range of this function. The curve gets close to y equals 3, but looks like it doesn't touch it, okay? I wonder if that's true. Well, that sort of introduces the one feature that shows up in the graphs of rational functions that you don't have in the graphs of polynomial functions, and these are called asymptotes. So asymptotes are straight lines, okay, either vertical or horizontal. Actually, they can also be tilted, but we're only going to look at vertical and horizontal asymptotes. All right, so an asymptote is a straight line that the curve is going to approach, okay, as either x gets really large or well, let me say it properly, okay? So because I'm going to say it wrong if I try to improvise here, right? So a vertical asymptote is a straight line, a vertical line, so it has an equation of this form: x equal to some constant, right? And what happens is at a vertical asymptote is the y values are going to get close to either a positive or negative infinity as your x values get close to this constant. This arrow here, that's a bit of mathematical notation that you're going to see again in calculus. And what that means is approaches or gets close to. So y approaches either positive or negative infinity, gets close to positive or negative infinity as x approaches this given constant. If that's true, then you have, again, what's called the vertical asymptote at that constant. All right, so that's what's happening in the graph of, notice that's what's happening in the graph of our first example here. We had a vertical asymptote at x equals -2, right? Because as your x values get close to -2, right, as your x values get close to -2, notice your y values are approaching or are getting close to either positive or negative infinity, right? So as your x values get closer and closer to -2, they can't touch -2, by the way, because -2 is not in the domain, right? But as your x values get close to -2, notice here your y values are getting close to positive or negative infinity. That situation describes what's known as a vertical asymptote. Now, for a horizontal asymptote, what's happening is as x is getting close to positive or negative infinity, your y values are approaching some number. So see, that's what y'all told me in this picture, right? As x gets really large, as x gets close to positive infinity, what are your y values getting close to in this graph? What'd y'all say? You thought was what? 3, right? the y values you thought were approaching 3. Or as x gets really small here, as x goes down to negative infinity, same thing, right? Tell me the y values were approaching 3, right? That situation describes what's called a horizontal asymptote, right? The y equal 3 would be the horizontal, would be the equation for the horizontal asymptote. That's what these notes say, all right? So you have a horizontal asymptote, that's a line. So since it's horizontal, it has an equation that looks like this, y equal to a constant. So you have a horizontal asymptote if, as x approaches either positive or negative infinity, if your y values get close to this horizontal line, that's called a horizontal asymptote. And that's going to be a common feature of rational function graphs. They're going to include horizontal and vertical asymptotes. Well, let's try looking at another one, right? So here's the problem. We want to determine the horizontal and vertical asymptotes of this rational function. Now, I haven't told you how to do this with pencil and paper, right? So our only choice here is to maybe try what? Graphing. Except the vertical asymptotes you can discover with already with just pencil and paper, because you know the vertical asymptotes are going to occur at numbers that are not in the domain. So how do you find numbers not in the domain? What do? Set the denominator to 0. So we can find the vertical asymptotes just by setting the denominator to 0. Well, let's do that and see if we can solve that equation. Notice that's going to be a polynomial equation, right? Because the denominator is a polynomial. So we're really just finding zeros of polynomials here, but now y'all know all about doing this, right? Can y'all solve x squared minus 2x plus 1 equals 0? That one is easy because I think it factors, doesn't it? Yeah, it factors as x minus 1 times x minus 1. And so it looks like the only solution there, what, is x equal 1? So there is your one vertical asymptote there, x equals. So the graph will not cross over x equals 1. Here I have we'll blow this up in a moment here, but here's a little picture of that graph. And this line right here, that must be x equals 1, right? Because that we know is the vertical asymptote. So see what happens as you're getting, as x gets close to 1, either on the left or the right. As x gets close to 1, what happens to the y values? The y values are getting close to what? In this case, close to what? What are the y values shooting up to? Infinity, right? Okay. We'll look at the graph on Desmos in a moment and confirm that. Now, what I don't know, however, are if there are any vertical asymptotes. So we're just going to have to look at the graph and hope for the best. All right, let's look at that graph. There it is. Let me pull it over. Oh, so there's that picture. And so we know we have this vertical asymptote right there at x equals 1. So as your x values get close to 1, your y values in this case are getting close to what? Infinity? Now, we're not sure of this, but it looks like there is a horizontal asymptote too. What does it appear to be? Y equals 2, right? Okay, because as x is getting really large, right, it looks like this curve is falling off to y equals 2, right? Same thing on the left, right? As x gets really small down to negative infinity, it looks like the curve is falling off to, again, to y equals 2. So it looks like we do have a horizontal asymptote there. So we're not sure of it, but that's certainly what it appears to be from the picture. How can we write this down on paper? So if you want to show me on paper that there's a vertical or horizontal asymptote, here's what you would write. You would say as x approaches or gets close to 1, this is the vertical asymptote. then what's happening to the y values? What do you see in this picture as x gets close to 1? What's happening to the y values? Yeah, y is approaching infinity, okay? And it looks like as x is approaching either plus or minus infinity, then what is y approaching in this picture? So that is the horizontal asymptote. So as x goes to positive infinity, or as x goes to negative infinity, what are the y values getting close to? What'd y'all say? 2. Remember the picture? Yeah, see, as x is going down here to negative infinity, here it is at negative 16, right? But as it goes further and further to negative infinity, it looks like the y values are dropping off to positive 2. Same thing here on the right-hand side. As x gets close to positive infinity, it looks like your y values are getting closer and closer to 2. So this situation describes a vertical asymptote. The second situation describes a horizontal asymptote. So we know for sure where the vertical asymptotes are because we can do that. We can find those with pencil and paper by setting the denominator to 0. This is the one we're not sure about, right? So we're just kind of guessing that we have this horizontal asymptote 2. Well, we're going to take the guesswork out of it because it's really easy to figure out what the horizontal asymptotes are. That's actually easier than finding the vertical asymptotes, all right? So I'll show you that next. But let's take our break first, okay? So we'll come back at 11:26 or 7, something like that, all right? And I'll show you the trick here for finding the horizontal asymptotes because they're really simple. So you will like that. All right, so I'm going to pause the recording. All right, so we're back. And so let's scroll down in the notes there. I'm going to show you the recipe now for finding horizontal and vertical asymptotes for rational functions. So here's a rational function written out kind of in grisly detail, right? Remember, it's going to be a polynomial divided by a polynomial. So this is what polynomial formulas look like, right, in abstract, right? Remember, it's just powers of x added together, right? But you may have, of course, different coefficients on the different powers of x. The degree of the top and the degree of the bottom can be different, right, in a rational function. They don't have to be the same. So in this diagram, the degree of the numerator is n, and here the degree of the denominator is m, correct? So we already mentioned that to find the vertical asymptotes, right, that means you're going to set the denominator to 0. So that in other means you're going to be finding the zeros of this polynomial that are in the denominator, right? So your vertical asymptotes are just the zeros of the denominator polynomial, because those are the numbers that cannot be in the domain of the function, right? So that's why you have breaks in the graph at those values. Those breaks are what give you the vertical asymptotes. Now, so you know, theoretically easy, right, to find the vertical asymptotes. Just find the zeros of the denominator. What are the zeros of the numerator? What do they tell you, by the way? Which is not in this diagram because it has nothing to do with the asymptotes. But what do the zeros of the numerator tell you for your rational function? Remember, how do you find the x-intercepts of a rational function? You set the numerator to 0. So the zeros of the numerator here will be the zeros of the rational function as well, right? The x-intercepts of the numerator will also be the x-intercepts of the rational function. But that has nothing to do with asymptotes. Now, what about for the horizontal asymptotes? How do we find those? Where horizontal asymptotes occur? Okay, so it's very simple. All you have to do is compare the degree of the top and the bottom. Okay, that's what the horizontal asymptotes depend on, are the degrees of the top and the bottom. So, of course, those can be different, right? So there's three cases you have to consider. If the degree of the top is less than the degree of the top is less than the degree of the bottom, so say you had x squared over x cubed, something like that, right? Top less than bottom degree. Then what happens is you do have a horizontal asymptote. It's the x-axis. The x-axis becomes the horizontal asymptote. The x-axis is a formula, by the way, is y equals 0. That's the formula for the x-axis. So if the top degree is less than the bottom degree, y equals 0 is going to be the only horizontal asymptote. So that's the same as the x-axis. So what that tells you is your y values are going to approach 0 as x approaches positive or negative infinity. Or you can write this backward. As x approaches positive or negative infinity, y is going to approach 0. All right, now, so there's one case. Now, the opposite of that, right, would be if the degree of the top is bigger than the degree of the bottom. So what if the top degree is bigger than the bottom? So suppose we had x cubed over x squared, for instance, right? Top degree bigger than bottom degree. Then that's even better. You don't have any horizontal asymptotes in that case. All right, so there aren't any horizontal asymptotes in that situation. So that's kind of an easy case. And then finally, the third possibility, of course, is that these two degrees are equal. So you might have a quadratic divided by a quadratic or cubic divided by a cubic. In that case, you do get a horizontal asymptote. You do get a horizontal asymptote. And the way you find it is the value of the horizontal asymptote is just take the quotient of the leading coefficients. So you take the top coefficient divided the top leading coefficient divided by the bottom leading coefficient, and that's going to give you the value for the horizontal asymptote. That's what this line in the middle here says, right? So if the degrees are the same, then just take the quotient of the leading coefficients. That's going to be the where the horizontal asymptote occur. All right, let's check that now, because let's go back to our prior examples and see if we believe that. So we said here, we thought we had a horizontal asymptote at y equals 2, right? So let's check that. So what's the degree of the top? 2. The degree of the bottom is also 2. So those are equal. So that means you may have a horizontal asymptote, or you will have a horizontal asymptote if you take the leading coefficient divided by the leading coefficient here, leading coefficient of the top divided by the leading coefficient of the bottom. Well, that's 2 over 1, which is what? 2. Yeah. So we were right. We did have a horizontal asymptote at y equals 2. As x approaches positive or negative infinity, y is approaching 2. Or you could write this backwards. Y approaches 2 as x approaches positive or negative infinity. What about the first example? That one also had a horizontal asymptote, right? At, what did y'all tell me? 3? So y'all thought it was 3. Is that correct? Well, what's the degree of the top here? 1. Degree of the bottom is also 1. What's the quotient of the leading coefficients there? 3 over 1. So y'all read the graph properly. There is a horizontal asymptote there at y equals 3. So you could write that down. Of course, you could just write it. Horizontal asymptote. Oh, by the way, here's how you spell the word asymptote. This is a hard word to spell. So it's asymptote. So we have a horizontal asymptote at y equals 3 as x approaches positive or negative infinity, then y is approaching 3, right? Or you can write this backwards. You could say y is approaching 3 as x approaches positive or negative infinity. Well, let's try just a couple more examples here and see what we can discover. All right, so let's see if we can find the horizontal and vertical asymptotes for this rational function. Let's write down everything. In fact, let's write down what we can about this rational function. So first, let's write down what the y-intercept is going to be. What is the y-intercept going to be here? Yeah, you said it right. Yeah, how do you find y-intercepts? You do what? Plug 0 in for x, right? So when you plug 0 in for x into this formula, you have to look carefully what happens. All these terms disappear and you just get left with what? 21 over 25? So we have a weird y-intercept there, 21 over 25, whatever that is. What about x-intercept? So how do we find the x-intercepts? Yeah, set the numerator equal to 0, right? And then solve that equation. So we get what x is what? Minus 21 over 25? Which is that what? Minus 4.2 or something like that? Minus 4.2? So we have x-intercept there. Minus 21 over, not 25, but 21 over 5. Okay, so know that. Now, what about the horizontal and vertical asymptotes? So let's start with the vertical asymptotes first, because those might be the hardest ones to find, right? How do you find the vertical asymptotes? What do you have to do? Set the denominator to 0, right? Because you're looking for numbers that are excluded from the domain, right? Remember, that's where you're going to be dividing by 0. So you set the denominator to 0. And that's not so hard to find the solutions to this equation because you can factor, right? So that's just x plus 5 times x plus 5, right? So there's only one solution, x equals -5. So we do have a vertical asymptote at x equals -5. So vertical asymptote at x equals -5. So what does that mean about the graph? That means what? Y is approaching what? Plus or minus infinity. We'll have to look at the graph and see which one it is, right? As x approaches -5. Yeah. Okay. So y is either shooting up to positive infinity or it's falling off to negative infinity. We'll have to look at the graph to see as x approaches -5. That's the vertical asymptote. Now, what about horizontal asymptote? No equations to solve here. So what's the degree of the top? 1, not 0, 1. What's the degree of the bottom? 2. So degree of the top less than degree of the bottom. So what happens in that case? Paul? Y equals 0, right. The x-axis, y equals 0, is the horizontal asymptote. So you have a horizontal asymptote. At y equals 0, in other words, the x-axis. So what that means is y is going to be approaching 0 as x approaches plus or minus infinity. Or you could write this backwards, as x approaches plus or minus infinity, then y is going to approach, oh, not infinity, what did I say? 0, right? Well, let's check that now and see if we got some of those things right. So let's look at the graph. I have a graph here. That's it, right? Yeah, that's the formula. So let's turn that one on. Ooh. All right, so we get a funky graph here. Sometimes if you position things just right, because of the way Desmos draws graphs, it will draw the vertical asymptote for you. It's kind of flat. Oh, there it is. There's the vertical asymptote. What was that supposed to be? X equal -5, right? Okay, so there's our vertical asymptote at x equals -5. In that case, notice that y is falling off to -infinity, right? As x is approaching -5. And then what's happening on the far left and on the far right? On the far right, what's happening to the y values? They're just falling off to what? To the x-axis, right? They're just falling off to 0, right? And same thing happens on, you may have to scroll quite a bit to see it, but same thing happens on the left-hand side, right, as well. As x gets really small, as x goes down to -infinity, again, y is getting close to the x-axis. Y is getting close to 0. Just exactly as we expected. So this one is nice. This one has a turning point. This rational function has one turning point on it. There it is. Okay. That would be interesting to find that one. Desmos says it's -3.4. Calculus, you'll learn how to find that. It's not going to be easy though. Okay. I'll promise you that. Not easy. Much easier for the polynomials. Okay, let's try a couple other examples then. Let me let y'all try one or two. Okay, so tell me about this function. Don't worry about the intercepts here. Okay. What are the horizontal and vertical asymptotes? Is there a vertical asymptote? Where is it? Is there a horizontal asymptote? What is it? You guys do this at home. So for that function, what are the asymptotes? I'm not worried about the intercepts. The X-intercept there, I think, is hard to find. I should take like a minute. So if you have this one on the test, then huh? No, I'm asking to find the horizontal and vertical asymptotes. Yeah, okay. So that's a rational function, polynomial divided by polynomial. So it may have some horizontal and vertical asymptotes. What are they? Of course, maybe it doesn't have horizontal and vertical asymptotes. Rational functions do not have to have vertical asymptotes either. They don't have to have horizontal ones or vertical. Well, I've seen examples where they have asymptotes, but they're not required. Okay, so this should be really quick. So where do you have a vertical asymptote? You want to be able to do something like this on the final exam. This is on the final exam, right? So you want to be able to do something like this on the final exam really fast. So we have a vertical asymptote it's vertical, so it's going to be x equal to a number. Where is it? 2, yeah, okay. So again, remember, you find that just by setting the denominator to 0, right, and solving. So you're just solving x minus 2 equals 0, which means x equals 2, okay? So this tells us what? That y is going to be approaching plus or minus infinity, right? As x approaches 2. we'll look at the graph in just a second and verify that, but that must be the case, right? Because obviously 2 is not in the domain of this function. So you have to have a break in the graph right here at x equals 2. What about for horizontal asymptotes? There isn't one. Yeah, that's also, that's nice, right? Okay, because the degree of the top is 3, the degree of the bottom is only 1. So no horizontal asymptote. Yeah, no horizontal asymptote. Let's graph it and just verify that one. So is that this one? Yeah, I think so. So wow, boring there, right? Not as boring as I thought. If you zoom out a little bit, there are 2 pieces there, right? Okay, and they're split up by this vertical line, which of course is x equals 2, right? But notice no horizontal, don't see any horizontal asymptotes there, right? Okay, as x gets really large or as y gets really large, this is not approaching a horizontal line, right? Okay, you do have a turning point though. Turning point right there looks like it. Ooh, wow, 2.74. So I wonder how that turning point came about. So we do have a turning point right there. These are, I don't think these are turning points. So you have some bends in the graph right here, but you don't have any turning points right here. Just because you have a bend does not mean you have a turning point. Students often want to point right here and say this is a turning point, but because you have a turn there, right? Okay, in the graph, but that doesn't make it an official turning point. How do you get an official turning point? It has to switch from what to what? Yeah, well, nope. It's, yeah, change in slope. Another way of saying that is change in direction. You have to have a change in direction. It has to switch from increasing to decreasing or vice versa. See here, it's switching from decreasing to increasing. So you definitely have a turning point there. But here, it's not switching, right? It's always doing what? It's always decreasing, right? As you move from left to right, the y values are always falling here. They're not always falling at the same rate. Sometimes it's dropping really fast, and sometimes it's not dropping as quickly, but it's still always decreasing. So you don't have any turning points here on this side of the graph. All right, let's try another one. This one's it's a good graph, but not interesting in terms of asymptotes, right? Okay. So I think I have one more here. Do I? Yeah, there's the graph again. Okay, so y'all do this one. So find again the horizontal and vertical asymptotes. I don't think I have a, see if I put it down here. No, I don't. I don't have a graph of this one. Darn. Maybe I do. All right, you people at home, did y'all find a horizontal asymptote? Someone on Zoom there, did you find a horizontal asymptote? Horizontal, not vertical. So the horizontal ones are always easy to discover. So that will be the easiest problem in the class. Ah, got it there. Fernando and Mohammed, thank you. You're right, 1/2, right? Y equals 1/2. And so how do you guys know that? Fernando and Mohammed, how do y'all know that?
The two leading exponents on the coefficient are equal, so just be dividing.
That's right. So the degrees are the same, right? The degree of the top is 3. The degree of the bottom is 3. And so you just take the quotient of the leading coefficients. So the leading coefficient on the top is 1, and on the bottom, it's obviously 2. So you have a horizontal asymptote at y equals 1/2, right? Okay. So that means that y is going to approach 1/2 as x approaches plus or minus infinity. As you go far to the left or far to the right on this graph, the y values, the graph, the curve itself is going to get close to this this horizontal line, y equals 1/2. So the graph sort of flattens out there, and y equals 1/2 on the far left and on the far right. Now the vertical asymptotes are trickier, right? Okay, in this case, but not too bad. So we find those by taking the denominator again, right? And setting that to 0. So tell me how to solve this equation. That's a polynomial equation, right? So how do we solve this one? Factor out 2x squared. Perfect, right? We're going to try solving this one by factoring because it does factor a little bit, right? You can factor out 2x squared. So you get 2x squared times what? X minus 2, is that right? And now your solutions are obvious, right? One solution is x equals 0. And the other one is what? X equals 2. Oh, perfect, right? So we do have a couple of vertical asymptotes at these two values. And so this means two things, right? Y is going to be approaching plus or minus infinity as x approaches 0. And also y is approaching plus or minus infinity as x approaches 2. Yeah, I don't think I have a graph of this one, so I think we can verify this one. Let me see. I do. Oh, darn it. Okay. Well, so we'll just have to trust our analytical skills, right? To know that we have the right asymptotes. All right. Well, now we've arrived at the ultimate topic here for the class. All right. Not ultimate in the sense that it's the best, but it's the final one. Okay. And so this is what I promised right before class, right? That we're going to start talking about a different coordinate system other than the rectangular coordinate system. So we've really been harnessed to the rectangular coordinate system all semester, right? So we've been talking about a lot of X's and Y's, correct? Okay, because those are associated, right, with X and Y values are associated with locating points, right, on the rectangular coordinate system. But we have other methods for locating points on a two-dimensional surface other than the rectangular coordinate system. So I'm going to show you an alternative method today, okay, which is also very useful in certain situations. So the rectangular coordinate system is certainly useful, right? Okay, but this new coordinate system is also useful, and this is called polar coordinates. All right, now let me show you how this works. It's intuitively very kind of obvious though. So suppose you have a two-dimensional surface, right? Like the computer screen here, and of course in the rectangular coordinate system, right? To locate points on that two-dimensional surface, you draw your set of axes, correct? So you draw your x-axis, and then perpendicular to that, right? You draw your y-axis, and of course those are just number lines, right? And we usually draw them so that they both intersect here at 0 on both number lines. That point where the two number lines cross each other, right? Where the two axes cross each other, that's called the origin of the coordinate system. And usually you draw your coordinate system so the origin is located at point 0, 0, right? Okay. And then if you want to describe the location of a point in the rectangular coordinate system, right? You write down two numbers. It's so-called x coordinate, which gives its relative location according to the horizontal number line, right? Usually called the x-axis. And then you write down the second number, which gives its relative location according to the perpendicular axis, usually called the y-axis, right? And so those two numbers together, right, you can use them to find where the point is located. So that's just normal old vanilla rectangular coordinates attributed to Descartes, okay, or devising this system, but probably it wasn't really Descartes that. All right, so now, but let me show you another method. So in our second method called polar coordinates, so we still have a two-dimensional surface, but in polar coordinates, we're only going to draw a horizontal axis. All right, and actually our horizontal axis is only going to be the positive half of a number line. Okay, actually the non-negative half of a number line, because we're going to start at 0. So this dark green area here is the axis that you draw. It's a horizontal line in the polar coordinate system. So you only get a one axis, which is a little bit feels a little bit disorienting, right? Okay, because you don't have two axes. Now, very honestly, in most cases, when you're using polar coordinates instead of rectangular coordinates, you go ahead and draw both axes anyway, right? But technically, you only have to draw one, which is the non-negative half of a number. This is not called the x-axis. This is called the polar axis in polar coordinates. All right, now, how do we locate a point in this weird system where we only have this half a number line as our axis? All right, so suppose I want to give the location of this point in polar coordinates. Same point that I was locating before in rectangular coordinates. All right, here's what you do. Just draw a line out from the beginning of your number line, okay, at the beginning of your polar axis to that point. All right, so that's this little dashed line that I've drawn here. By the way, that 0 on your polar axis, where your polar axis starts, that's called the pole. So the pole is kind of like the origin for rectangular coordinates, but in polar coordinates, it's referred to as the pole. All right. So I've drawn this line here from the pole out to my point that I'm trying to locate in the polar coordinates. Calculate that distance then. Okay, of course, there's going to be a distance there, right? I'm going to call that, just for notational purposes here, let's call that that distance r. All right, so short for radius, but now once you've drawn that dashed line here, of course, then you've created an angle, right? You've created an angle between your polar axis and this line you've drawn from the pole to your point. All right, of course, that angle has a measure, and I'm going to call that measure theta. So here it looks like theta is what, maybe 60 degrees or something like that. So in radians, that would be, in radians, 60 degrees. Pi over 3, right? Okay, yeah, right. So in radians, that's pi over 3. So to locate this point, all you have to give is this distance and this angle. So notice you still have two coordinates for your point, but the coordinates here in polar coordinates mean something different. The first number is the distance from your point away from the pole, and the second number is the angle formed by this line and the polar axis. So think about it. If you know these two pieces of information, the distance at a point is away from the pole, and then this piece of information, the angle formed between that point and the polar axis, then you can figure out where the point is located, right? Okay. So again, in polar coordinates, it requires two pieces of information to locate this point. Why does it require two pieces of information? That's exactly the same as that's exactly the same amount of information as we required in rectangular coordinates, right? We also needed two pieces of information, correct? Why is that true? Look, you know, this, okay, all right. This is just something, this has to do with the nature of the universe, right? Okay, so I can't explain to you why this is true. It requires two pieces of information because this is a two-dimensional surface, right? Okay, two-dimensional surface. To locate a point on a two-dimensional surface, you're going to have to use two pieces of information, all right? Okay, so that's just the way our universe works. All right, so so there it is. That's how coordinates work in polar coordinates. Now, since we're so used to working in rectangular coordinates, right? We've been using the rectangular coordinate system probably since you started plotting points on two-dimensional surfaces. So you're very accustomed to that system. So it's very important for us to be able to convert back and forth between polar coordinates and rectangular coordinates. All right, especially when we're first beginning to use polar coordinates. So I want to show you how you convert back and forth, right, between rectangular coordinates and polar coordinates. And a little trigonometry goes a long way here. So look at this picture will tell you everything you need to know. In this picture, right, notice I have this right triangle, correct? Okay, this right triangle that I formed. This line, of course, is the hypotenuse. And then I just dropped this vertical line down from my point. Of course, what's the length of this vertical line? Well, in rectangular coordinates, that length is going to be y, right? Okay, and then what's the base of this right triangle? Well, that's going to be x, correct? Right? Depending on where this point is located. So this length is y and this length is x. So using trigonometry, right? You know, you can compute the cosine of theta, right? You can compute the cosine of theta by doing what? Taking, how does that work? Cosine of theta is what? Opposite over hypotenuse. Is that right? No, adjacent over hypotenuse, right? Okay, that's I was thinking of sine. So cosine is adjacent over hypotenuse. So notice then in this picture, the cosine of theta is going to be x over r, right? X over r. Remember, I called this hypotenuse r. So you get this equation, cosine of theta is equal to x over r. And now if you solve this for x, just multiply both sides by r, right? Oh, so you get this equation, x is equal to r cosine theta. Oh, so notice what that tells you, right? That tells you, if you have a point given to you in polar coordinates, how can you convert it back to rectangular coordinates? Well, to find the x coordinate in rectangular coordinates, just take r times cosine theta. That will give you the x coordinate in rectangular coordinates. And you can play the same game by taking y divided by r. That would be the sine of theta, right? And so sine of theta is y divided by r. If you multiply both sides by r, you get that y in rectangular coordinates is r times the sine of theta. So if I give you a point in polar coordinates and you're trying to figure out, gosh, where's that point at? Okay. If you want to convert it back to rectangular coordinates, you can just use these equations. X is going to be r times the cosine of theta. R is always this first value here, right? Times the cosine or the sine of the second value. Remember, the second value is an angle. Now, what about going from rectangular coordinates to polar coordinates? So suppose I give you a point in rectangular coordinates and I ask you, okay, what's the polar coordinates for that point? How could you figure that out? Well, let's see. What do we need for our polar coordinates? We need to know this distance, right? The distance from the pole or the origin to the point. So we need to calculate this distance. But you can do that from the Pythagorean theorem, right? Because in this right triangle, what do you know? X squared plus y squared has got to be what? This hypotenuse squared, right? R squared. Take the square root of both sides. Oh, there's the R value in polar coordinates. It's the square root of x squared plus y squared. So if you know the rectangular coordinates, if you just take the square root of the sums of the squares of the two coordinates, that gives you the R value for polar coordinates. Now, what about the angle? Well, the angle is a little bit harder. Let's see if we can figure out how to find this angle. Let's see. Look at this picture. In this picture, there we have theta, right? Notice if you compute the tangent of theta, how would you compute the tangent of theta from this picture? That's opposite over adjacent, right? So in this picture, that's y divided by x. So how do you find just theta? How do you solve this equation for theta? What do? Apply what? Yeah, you apply the inverse to both sides. So you apply the inverse tangent. Oh, so there it is. If you take the inverse tangent of y divided by x, that's your rectangular coordinates, right? So if you take the y coordinate divided by the x coordinate, take the inverse tangent of that, that's going to give you the theta that you can use in your polar coordinates. Yes. Oh, yeah. You were going to remind me about it one time. Okay, so look at these formulas. I've got them boxed off because these are important. If you want to convert between rectangular and polar coordinates, if you know the polar coordinates, you can use these two equations to find x and y, the rectangular coordinates. If you know the rectangular coordinates, you can use these two equations to find the r and the theta, the polar coordinates. Remember, what's the r? It's a distance, right? What's the theta? As usual, it's an angle, right? Okay. All right. Now, before we actually apply these equations, though, let's do something a little bit simpler. So let's try plotting points in polar coordinates. So just something really elementary, so we can get a better feel for polar coordinates. So these are points written in polar coordinates. So the first number is a distance. The second number is an angle. So here's my there's my polar coordinate system. And remember, technically, you only really need this this positive horizontal axis, right? Or this non-negative horizontal axis. Remember, that's called the polar axis. But almost always, you're going to go ahead and write. You're going to draw the full set of axes. There are a vertical one and a horizontal one when you're using polar coordinates. All right, now let's see. What point was I supposed to plot there first? 1 and 3 pi over 4. These are going to be given, your angles are going to be given in radians. They're usually not given in degrees in polar coordinates. So you have to, just resign yourself to working in radians. So 1 and 3 pi over 4. So where is that point going to be at in this picture? So first, that point forms an angle of size what? 3 pi over 4, right? So where's 3 pi over 4? Is that in the second quadrant? That's over here, right? Oh, so that's nice. We know that point 1 and 3 pi over 4 is somewhere on this line, okay? Because all of the points on this line form an angle of 3 pi over 4, right? Now, of course, we only want one point on that line, right? And we want the point. So what's the point we want? What's happening? Is someone signing in the wrong place? Yeah, who's signing? Is that Alexander signing in the wrong place? Alexander, you're always signing in the wrong place. Yeah, your place is 15. Okay, yeah. So should have signed there in 15. So do that. Well, you only got one more chance to sign. So on Monday, sign in 15. All right. Okay. All right. Now, so we know the angle to our point is 3 pi over 4, right? But so that's over here in the second quadrant. In rectangular speak, that's in the second quadrant. But in but there are lots of points that form an angle of 3 pi over 4, right? So we want just one of those points. And so how do we know which point to pick out there off that line? What do we know? Its distance has to be what? 1. So you have to try to find the point on this line that's at distance 1. Okay. Where would that be at? Maybe about, well, there's 1. So that length is length 1. So try to duplicate that on this line. I think it's about right there, right where I put the arrow. Does that look about right? See, there's length 1. So if I go along this line, that same length, oh, I think it's going to put me right about there. So there it is. I think that's the plot of 1 and 3 pi over 4. Right about there. So let's try another one. So now 3 and minus pi over 6. So where is minus pi over 6? How much is minus pi over 6? Negative 30. So we're down here somewhere, right? At minus 30 degrees, maybe somewhere along this line, right? But we want to be at distance what? From the pole? 3. So this is where it's hard to estimate. What along this line is distant? Don't put it right here. Okay, that's distance 3 on the x-axis. But what would be distance 3 along this line? Okay, maybe I think maybe about right there. 3. So you want this distance to be 3, right? And then this angle, want that to be minus pi over 6. What? Oh, yeah, I did.
Okay.
And I put a 6 there. So this is what it's kind of tricky to plot points in polar coordinates. Plotting them is sometimes tricky. But you know, because getting the angle exact is hard, right? And then also finding this distance, right? This straight line distance from the pole to your point, it's hard to estimate if it's not horizontal and vertical. It's hard to estimate that distance properly. Now, you can find polar graphing paper that makes this easier, okay? But here since we're just graphing on this rectangular graphing paper, not so fast. Let's try one more. 5 and 3 pi. This one's pretty easy, I think. So where would 5 and 3 pi be? What's the angle 3 pi? What does 3 pi do? Let's see. It's past 2 pi, right? 2 pi is 1 revolution, and then it's another pi, which is what? Another 180 degrees, right? So that puts you right there, right? And then we only going to go what? Distance what? 5, yeah. So go distance 5 out here. So that's going to be symmetrical with this distance. So that would put us about right there, I think. So here is 5 and 3 pi. Now, polar coordinates have, let's do the last one before I get into the issue with polar coordinates. The last one is interesting. because it has a negative distance. Now, we don't think of distance as being negative, right? Okay, but you can plot this point. You just have to think of that negative distance in the right way. The angle, though, is pretty easy. What's the angle? Is pi over 4, which is what? 45 degrees, right? So if you draw that 45-degree angle, it comes up like this, right? Here's pi over 4. But how would you interpret the -4 in this case? Yeah, Evan, you're right. You're going to go this direction. Instead of going here along the angle pi over 4, you'll go the opposite of the angle. So you would come down here along the same line, but then mark off a distance of 4, maybe about right there. So here would be -4 and pi over. +4 and pi over 4 would be up here. -4 and pi over 4 turns out to be in the third quadrant, this direction. All right. Now, one of the issues with polar coordinates, they're hard to graph, okay, right? Because you're used to graphing in rectangular coordinates. Another issue with polar coordinates that's a little bit annoying is in rectangular coordinates, every point only has one pair of coordinates. Every point has one pair of coordinates. But in polar coordinates, not true. Okay, points can have different coordinates. The same point can have different coordinates. All right. So you can plot different coordinates and come out at the same point in polar coordinates. That doesn't happen in rectangular. So that's another kind of complication with polar coordinates, but that doesn't make them useful, right? In practice, they're extremely useful. There are many applications where polar coordinates for locating points turned out to be more beneficial than using rectangular coordinates for locating points, okay? All right, so I've run past time, so we'll stop there and continue talking about a little bit about polar coordinates next time. So don't forget about your homework that's due tonight, and then you got another one due Monday, right? Okay.